triangle. I'm very lazy there, sorry. Got my three-dimensional picture again. On your own time, you can experiment with changing your x and y, like how flattened out that x and y is, just to kind of see like how things change with a little bit of, like see I really flattened this one out quite a bit. Like that one I don't think I flattened quite enough. But either way, you can kind of mess with the different perspectives. But here it comes. So we've got my parabola going that way, and a parabola going this way. And then I've got my little piece here, and that's going to form an equilateral triangle, right? So let's take a look at that equilateral triangle. Put it up here. It's got some thickness to it. We need the area of that, don't we? So what's the area of that triangle? 1/2 base times height. We all agree with that? Now, do we know this? Do we know this right here? That's the base, right? So that's 4 minus 2x squared. That's what we had. So you're saying that if I have this triangle, the base was 4 minus 2x squared, and that the area of that is 1/2 base times height. Yeah? Okay, what's the problem we run into with that formula? The height, right? Do you know the height? The height is the distance from here to here, right? That's height. You don't know what that is. It's not given to us, right? It's not obvious. Do what? The height does change, but it changes as a function of x. So as x changes, the height changes. What I'm getting at is that I can't just leave h here in my formula. Like I need to get this h somehow in terms of x. So that as x changes, I can see how the height changes. But right now, it's not in terms of x. So how could I solve for h if I wanted to use this? What's that? Pythagorean, right? So are you saying you could look at this as like a little right triangle right here? Just one side of it? Do y'all agree? So I could do this, kind of redraw my picture, and then say, okay, this is height, and then this side would be what? Half of this, right? So 2 minus x squared. And then, do you know this side? This is the entire equilateral, right? So that is 4 minus 2x squared. Agree? Then you could say like a squared plus b squared is c squared. And you could solve that for h, couldn't you? Y'all all on board with that? Okay. I actually don't like this at all, okay? I don't like that at all. It'll work, okay, but the algebra is too messy. Let me show you a better way. So if you'd like, go ahead, have fun. You can play with that. But we have a better formula. So let's go back to pre-cal for a second. Let's say we have a triangle and we know that this is base and we know that this is height of a triangle. Now notice this is not an equilateral triangle. This is just a general triangle, right? We know that area is 1/2 base times height. And we all agree and we all don't argue with that, right? Okay. But there's another formula for finding the area of a triangle that does not require you having the height. Anyone familiar with it? Let me tell you what you need. You still need the base, okay? But then you need, what? What's that?
Oh, I just said the answer.
1/2 what?
AB sine theta.
AB sine theta, that's the one. So AB sine theta, the way it works is this. If you know the angle, let's say you have a side, we'll call it B. But you also have another side, A. And you have the angle between those sides, theta. Then we have a new formula. The formula is 1/2 a times b sine of the angle. That's an alternative formula that we can create in pre-cal. Now, I'll just take 30 seconds to show you where it comes from because it's not complicated. All right, what's the difference between these two formulas? There's only one slight difference. This one has a and sine theta, right? As opposed to h. So like if I said, look, take this formula right here and replace h with a sine theta, then that's what we get here, right? That's exactly where this formula comes from. Look at this triangle. This is a right triangle right here. You see it? Okay. So if I asked you right now what's sine of theta, what would you tell me? Here's theta. Sine would be opposite over hypotenuse, right? So it would be h over a. And then solve that for h. And what do you get? H is, multiply both sides by a. H is a sine theta. So if I take that and replace it with a sine theta, you get that formula, right? Now, why is this formula going to be better for us in this particular problem that we're looking at here? Because it's equilateral, right? And what does equilateral mean? All sides are the same, but that means all angles are the same, which means that all these are 60 degrees. So I know that this is 60 degrees, right? And I also know that this is, what, 4 minus 2x squared, and this is also 4 minus 2x squared. So do you see I have two sides in the angle between them? Then the area of that is 1/2 base times height. I'm sorry, not, why did I just say that? Side times side, a times b is what I meant to say, a times b, so that's squared, right? 4 minus 2x squared squared, that's a times b. And then sine of 60 degrees. And sine of 60 degrees, on your unit circle, go to 60 degrees, grab your y coordinate, is root 3 over 2. Now, you would have got the same thing over here, but you would have never had to do any solving in Pythagorean identity. This is so much cleaner. So let's see, what is the area of this? We're almost done with this part. I'll put it right here. The area of that is, yeah, put those together. So root 3 over 4, and then 4 minus 2x squared squared. So the volume would be what? The volume would be this times the dx, right? So I think it's integral time. Now this formula only worked because it was equilateral, right? Okay. So to answer part C, are there any constants I can pull out for part C? Root 3 over 4, integral negative root 2 to root 2, and then whatever's left, 4 minus 2x squared, that quantity squared dx. Wait a minute, isn't that almost the same formula for the square when we did squares? That was squares, wasn't it? That was squares? That's equilateral triangles. Just happens to be some constant multiple of the same thing. Okay. Hope that makes sense. All right, now we're officially done with 7.2 and 7.3. If you came in a little late, I had put up here the assignment for 7.3, which is, I do not believe it's on our schedule. So those are the problems that you should do out of 7.3. Those all involve doing shells, method of shells.
For the homework problems for part 2, I guess, of 7.2, when
I thought it was already on the list of questions. I think number 38, was it 38 and 39? Yeah, 38 and 39. In actuality, like any problems 38 through 43 would be good practice. But you have to be careful because on some of those problems, they tell you that the cuts are perpendicular to the y-axis, not the x-axis.
Are we not going to be doing that?
Well, I'm not going to show it to you. I'm not going to show you a problem with the y-axis, perpendicular cross-section.
Is it testable?
I'd say it's testable if I ask it on the homework, which I don't. But I'm saying if you want to try 38 through 43, those are good exercises. See, what we want to start to do at this point is like, I've shown you shells, right? Like earlier today, but we only did this kind of shell, right? Wrapped this way. Like I never did an example of a shell wrapped this way. So we want to get to a point now where I'm giving you the basic idea, not necessarily showing you an exact example of how to do that, but you understand the concept enough that you could do it yourself. So imagine the same problems that we just did, but cutting the other way, and how would that change your formula? So I want you to explore that on your own, and you can do that if you'd like problems 38 through 43. Will I test you on it? I doubt I'll test you on that. 380. That's on 380. All right, 7-4. Ready to move on? Arc length. So if you go back and you think about all the things that we've been able to figure out using calculus at this point, I mean, if somebody gave us a general curve, Cal 1, we could go to a point, we could find the slope of the tangent line, couldn't we? Right? That's Cal 1, basically, find the slope of tangent line. Cal 2, we can maybe cut it at two places, drop down, we can find the area of that. We could wrap that around the x-axis, find the volume. We could wrap it around the y-axis, find the volume. We could wrap it around different horizontal and vertical lines, right? Find volumes. Now we're going to talk about something that seems like maybe we should have dealt with this earlier, but this is where it appears, okay? After we do volumes, we talk about the length of an arc. So when we talk about arc length, what we're doing is we're taking a curve. Does anyone have like a charging cable for their phone laying around? No, I don't need I just need the cable. That's all I need. There we go. There we go. Got it. Okay, here you go. So what we're going to do is we're going to imagine taking a curve, right? And we're going to go from A to B. So we're going to just look at it between two places like this. Okay, we're going to look right there. And we're going to ask ourselves, if we were to take that curve, let me exaggerate this a little bit more. This is not quite enough. It's not very interesting. Okay, so let's say we take that curve. Let's call that function f. We take that curve. See if I can get your thing to bend properly. Right, so we've got this curve sitting here. If we were to take this off the page, right, and straighten it out, and then measure that distance, right? So that would be about right there to there. So if I pull that curve off the page and ask myself, L, length, how long is that? That's called the arc length, all right? Understand? Now, how can we do this? And we have to do this using some, it's obviously going to involve an integral, okay? So we're going to be adding up a bunch of little things, right? So let's see what we do here. Let's do what we've been doing. I'm going to try and like do a little cut of a rectangle again, right? But this time I'm not going to draw the rectangle. Maybe I'll draw just to show you it's here. So I do like a little rectangle almost like this. And that rectangle gives me two little points on that curve, doesn't it? And I'd like to try and see if I can measure how long that little piece is between those 2 points. So what I'd like to do is zoom in on this now. So like zoom in, zoom in, zoom in. We're going to blow this thing up over here, all right? So when we blow this up, we've got some curve, right? And we've got our 2 points, right? I'd like to know how long that blue curve is, right? What I could do is measure the distance straight from there to there. And that would be an approximation, wouldn't it? Now that approximation would have some error in it because this curves and that's straight, right? And that means the red line's shorter than the blue curve. But if I do this and I make this rectangle thinner, right? I was going to say narrower? Yeah. I want to say more narrower because I know it's wrong. If I make this rectangle thinner, then those points start to come together, don't they? And you start to get less error. And if I can make the rectangle become infinitesimally thin, then basically the red and the blue are the same. This is exactly what we've been doing, right? When we start with the idea of a rectangle, but then we have an infinite number of them, that's the integral. So what I'm going to do is I'm going to try and approximate blue with the red. All right? Okay, so now let's see, how can we do this? Well, I think it's pretty natural for us to want to draw a right triangle here. Is that pretty natural right there? Yes? So I'd like to know what this side, this hypotenuse is, right? I'd like to know what it is. So that means I probably need to know what these sides are, don't we? Don't we need to know those? Okay, so what could I do? What could I do? Go back over here. Think about Cal 1. If I were at this point right here, in Cal 1, if I took the derivative, wouldn't it give me the slope of that tangent line? Yes? So that red line, the slope of that red line is y prime, which is dy over dx. Agreed? Yeah? So that, if I go to this point, and I know that this drawing doesn't look like it, but you have to understand we're in the infinitesimal here, okay? So like this blue curve is like so close to this red one because we're in the infinitesimal. I'm just doing this to exaggerate it for you. The slope of the tangent line is basically the slope of that red line in the infinitesimal. As we zoom in and this error becomes less, the slope of the blue curve is basically the slope of the red line. Do you all agree with that? You sure? Okay. So when we talk about slopes of lines, this, to get from this point to that point, this was always our change in x, right? Delta x, and this is our change in y. So as we let this go to the infinitesimal and we let this rectangle get real thin, then delta x changes to what? It goes from delta x to what? See if you remember this. I know I mentioned it maybe once. Maybe I can help you with this. When we were doing Riemann sums, we had said that b minus a over n was the width of each rectangle. And they would always be the same for each rectangle. And then when we let basically them become infinitesimally thin, this we replaced it with what? dx, okay? That became dx. So this distance from here to here, as this starts to shrink, this becomes dx, right? And this side right here, same thing. This starts to shrink, this becomes dy, all right? In the infinitesimal, as you take a limit and let the number of these cuts go to infinity. Yes? You buying this? Are you buying it or no?
Trying.
Okay. I mean, you try your best to understand it. At the end of the day, we're going to have a formula. I'm just trying to show you where the formula is coming from, all right? So if we can say that as we allow the number of these cuts to become infinite, that this is basically turning into dx and this is turning into dy, then the hypotenuse of that, this should follow the Pythagorean, right? So I'm going to call this right here little l. That's this hypotenuse. Because we're trying to find capital L, which is the whole thing, right? So would you agree that dx squared plus dy squared should be equal to little l squared, right? As long as I let the number of these cuts go to infinity, that would be true. And I'd like to know what little l is, because if I could find little l, that would be the length of one of these little cuts, right? And then I just add them up with the integral. So it's just like us finding a formula for the little triangle or the little semicircle or a washer or a shell. We're trying to find a formula for what it is we're trying to add up. We're trying to find a formula for this hypotenuse. Solve this for L, for little l. And what do you get? Little l is the root of dx squared plus dy squared, right? Right, that would be if I solve for L here. And then if I wanted to know capital L, I would do the integral of this, right? From A to B, and in this case, A would be, here and B would be here. Now we would have a major problem. I'm going to put it up here, but I want you to see the problem we would have at this point. L would be the integral from A to B of the square root of dx squared plus dy squared, right? That's what it would be right now? The problem is, on the outside, didn't we always have like dx or dy? Right? We don't have it there, do we? Not yet. We're about to have it. I'm going to force it. I'm going to make it happen. Ready? Here's how I'm going to do it. Take this expression right here. Okay, what did I do? I factored a dx squared out of this, right? So I pull the dx squared out of that, I get 1. Now I pull the dx squared out of this, but it didn't have a dx squared, so I had to divide by dx squared. So I got this. Now, because this is multiplication, dx squared, I can pull it out of the root as just what? Dx. So this is going to become integral a to b. Now dx can't come out, right, because it's not a constant. So I'll slap the dx to the back, and then what do we have here? Square root of 1 plus. Now, what's dy dx from Cal 1? I mean, that's the derivative, isn't it? So this is just y prime squared. Well, we don't know what this is yet. We don't know what this is yet. Yeah, you might be thinking trig sub, right? So look at this. This is kind of crazy. That if you want to know the length of a curve from one point to another, you're going to have to do an integral, right? But that integral is going to involve its derivative, right? It's always going to have the derivative. So if you're trying to find the length of a curve, you have to take the derivative of the function, you have to square it, you have to add it to 1, and then you have to take the square root of it. And then you have to integrate that, if you can, all right? Got it?
So that's the formula for arc length?
This is the formula for arc length. So the length of a curve, y equals f of x, is this formula. You can replace this with f prime of x if you want. Right? If you don't like to write y prime, you can write f prime of x. You could just leave it as dy dx. It's up to you. They're all they all mean the same thing in this case. You ready for an example? Hey, if I take a circle of radius r, what's its area? What's the area of that circle? Pi r squared. I proved that to you, right? Yeah. We actually showed that, didn't we? If we take a ball, solid ball of radius r, we proved that the volume of that was 4/3 pi r cubed, right? And do you remember that this was actually easier to do than that one was? Yeah. Okay. So the area of this is pi r squared. We showed that. The volume of that is 4/3 pi r cubed. We showed that. What we have not done, which seems easier, but we haven't done it, is to show that the circumference of a circle is 2 pi r. Have we? We haven't done that, have we? Do you think we could? Is the circumference an arc length? It is an arc length, right? It's the length of the arc that goes around this thing, right? So why don't we attack this the same way we attacked those? Couldn't we draw a circle, right, of radius r, so I'll make this point r here, and couldn't we just look at just this arc right here, that piece right there, and find its length, and then multiply it times 4, and that would give us the arc length of, the circumference of a circle, radius r? Yeah? Okay, let's do it. So what's the length of this? What do we have to do first? We've done this 3 times now. It's the 3rd time. So what do we have to do first? We will restrict the domain between 0 and r, right? What am I going to be integrating? I have a formula. Yeah, what's the function, I guess is what I'm asking you. What is the function I'm going to be using for this integral? Yeah, so we've done this a few times. We actually had to solve for that, and we said that y would be equal to the square root of r squared minus x squared. Does that look familiar? That was taking the general equation of this circle, x squared plus y squared is r squared. That's the equation of a circle of radius r centered at the origin, solving it for y, and getting that. Does that look familiar? Because we've done it now a couple of times. Yeah? Okay, so I need to use this curve between 0 and r, and I need to generate the arc length formula. With me? What's the formula require? What was that formula I just erased? It's square root of 1 plus the derivative squared. So I need the derivative of that first, right, before I even put the formula up here. What is the derivative of that function? Remember that x is a variable and r is a constant. So derivative of square root of something, this can be chain rule. Derivative of square root of something is 1 over 2 root of that something. So that's the first part of the chain rule. That takes care of the derivative of the root. Now the derivative of what's inside. What's the derivative of r squared? It's a constant, right? So derivative of that 0? Derivative of that? Negative 2x. So times negative 2x. The 2's cancel. And you just get negative x over square root of r squared minus x squared. Right? Yeah, so in the formula, right, it's that squared and then plus 1. So let me square that right now. Y prime squared will be that squared. So what happens on top? We just get x squared, right? It's positive because square negative. And then, ooh, that's real nice. That's just r squared minus x squared. Nice. Then we'll do plus 1, and then we'll have to take the square root of that, right? All right, no problem. I'm ready. Let's do it. That was all my scratch work. Here comes the formula. The length of that blue curve right here should be the integral from where to where? 0 to r, right? So what we're doing is we're cutting this up into a bunch of little infinitesimal pieces, right? And it's almost like coming off the top edge of that rectangle. So it's always like x is always varying between 0 and r. Okay, so I have square root of 1 plus that, x squared over r squared minus x squared, and then dx. That's just the formula. Now that integral does not look very nice, does it? Okay, so here's kind of a standard approach when you see something like this with these arc length problems. A lot of times this 1 plus this function, you want to put that together into one fraction. So we need a common denominator, right? Yep, so we're going to go r squared minus x squared on top here, r squared minus x squared on bottom, like just turning that 1 into that, and then combine them. So what would my new numerator be if I did that? Just r squared, right? Because it would be r squared minus x squared plus x squared. So just r squared on top. And then what about on the bottom? The r squared minus x squared? We good? dx on the outside here? All right, now, what about that? If I have a root on a fraction, I can do them separately? I can do root top and root bottom separately. And the top is a constant. So when I take the square root of r squared, I just get r. And it's a constant, so it can come out of the integral completely. So I have an r out here, integral. What was still there? I have this right here with a root, right? But it's on the bottom. So 1 over that? Like that, right? Now what? Now you could use trig sub. Or you could go to your formula sheets, and we actually have a formula that looks like this on our formula sheets. Square root of a squared minus u squared du. Go look for it. Someone tell me what formula that is. Because I don't want to sit here and do trig sub. Oh, forgot my 0 to r. Yes, what number is that?
16.
Formula 16. Do y'all see it? For those of you who have your formula sheets, formula 16. Okay, so according to formula 16, we're going to have r, that's this r, right? The antiderivative of that is arc sine of u over a. For us, u is x, right? So x over, and for us, the constant squared, is actually r, right? It's r squared, so that's like our a squared in the formula. So that's x over r. And then we're evaluating, remember this is a definite integral from 0 to r, right? We're evaluating this from 0 to r, right? So let's plug in r first. So this equals, we're going to get two things we subtract. So we have r out front times, now when I replace this with r, I get r over r, right? R over r is 1. Arc sine of 1 says, like, where on your unit circle is your y coordinate, because we're talking about sine. Where's your y coordinate 1? Pi over 2. So this is going to be pi over 2 here. And then we plug 0 in here. 0 over r is 0. And arc sine of 0 is saying where on your unit circle is your y coordinate? 0. That happens at 0. So this is r times 0 is just 0. So what's our final answer? R times pi over 2. But remember, that was only 1/4 of the whole thing, right? We only did this piece, right? So if I multiply that times 4, then the 4 and the 2 cancel, you get 2 pi r. There you go. So I've proven them all to you now. Area, volume, and circumference. And it's used, all of them have used different techniques, right? For the area, we needed our area formula. For the volume, we had to do a solid of revolution. For circumference, we had to do arc length. All right, let's see what time we got. Oh, 10:35, perfect timing. Perfect timing.
So then when we're finding an arc length, would it always be like try to work it out to one of those formulas of like 1 over square root of whatever?
Yeah, you know what? That example I did right there was not a good reflection of what you'll see on a test. I just really wanted to prove that the circumference is 2 pi r. Next class, we're going to do another arc length formula, or another arc length problem. What you're going to see next class is that when you do an arc length problem in general, the algebra gets really messy, okay? Because in order for the problem to work, you need to be able to integrate this, right? You got to be able to integrate that. And so if you start with the function as simple as this, just look at the sine curve, and you just take that first arc, right? If you want to know how long that was, right? How long that arc was, we already know the area under here is 1. I think we rotated it also. But if we want to know how long this arc is, we would have to do the integral from 0 to pi, because that's where it goes to. And then we would have to do the square root of 1 plus what? The derivative of that squared, cosine squared x dx. And all I can tell you on that is good luck, because that is not going to go without a huge fight. Now, if it was 1 minus cosine squared, then it would be easy, but it's 1 plus. And there's no basic substitution you can do. There's no integration by parts. There's no trig sub, it's,
Wolfram.
yeah, if you Wolfram this, let's see what would happen if I Wolfram this. Although,
It's pretty strong for
integrate square root 1 plus cosine x, oops, no, cosine x, that quantity squared. My guess is that this is going to give us some sort of error function. Yep. So it's giving us that this is equal to root 2 of e given x and 1/2, where e, like what the hell is this? Well, this is the elliptic integral. Okay, the elliptical integral. So elliptic integral, so this is what we call an error function in mathematics. Don't worry about that, okay? Basically what that's telling you is you can't do it by hand, okay? From 0 to pi. Now if I put actual numbers in there, it's going to give me a numerical answer. 3.82 is the length. Now the reason why it was able to do that, and I'm jumping ahead here, well, where the heck is it? Doesn't have more information? Okay, let me take the 0 to pi out of there. Let's see if it gives us more here. Come on. Wow, really? Yeah. Well, I'll tell you how it's doing it, okay? It's not using the error function. It's actually, it's rewriting this in its power series, which is what we're going to do in Chapter 8. And once it's doing its power series, then it can integrate the power series. And that's how it's getting that numerical answer of 3.82. I guess the moral of the story is that something as simple as sine x, finding its arc length, is not that easy. So we have to be very careful on how we pick our functions here, or else we're not going to be able to integrate them. So the examples I do in class, next class, you'll see that we have to just pick our functions carefully.
So be careful.
No. Be careful what? Or Google it, yeah. All right, that's it, right? Have a good day, everyone.
What is Gauss? Gauss is
Well, Gauss is a mathematician.